This is experiment 1, density of solids. So we're going to start with our objectives. I'd normally have you write these objectives in class so we get a good understanding of what we're trying to do. In some labs that we've done in the past, we've written hypothesis using our independent variable and making a statement, not a question, to come up with some kind of process to try to answer that. But in these labs, what we're trying to do is we're going to use objectives. This is what we're trying to get done. So although we could write a hypothesis, we're going to stick with objectives here. So the objectives basically outline what we're going to do, what we're going to try to accomplish. So in this lab, density of solids, what we're going to do is, number one, the objective is, and you should write these down, measure the dimensions of the four objects and calculate their volume. So we have four objects. As you can see, I have a cube, I have a rectangle, cylinder, and then I have I guess a different size rectangle. All right, so rectangle, let's say 1, rectangle 2, a cylinder, and they're made of metals or alloys. And I do have a known list of densities, okay, to try to figure out what the substance is. So the major focus of the lab is try to determine what the density of these objects are, and then from their densities try to come up with what the composition that makes those objects. So that's really the major objective. So objective 1 is to measure the dimensions of the four objects and calculate their volume. So we're going to come up with a volume. Now, if I move my calculator, we have the density formula, then we have a volume of a cylinder and volume of a cube, which is really the same as the volume of any rectangle if the dimensions aren't the same. So using our formulas of volume, we're going to measure with our ruler, okay, in centimeters the dimensions, length and width. And what's it going to give us? Because we're using volume, we're going to come up with centimeters cubed. So it's important that you realize that our volume is going to become in centimeters cubed. All right, and that's very important because when I take a shape like this, it's going to be some number of centimeters, let's say a wide, height, and width. Obviously, it's going to be a centimeter cubed. It's going to have length, depth, and width, and so will all the objects. Now, important, like page 10 of our notes, is a centimeter cubed is equivalent to 1 milliliter. And that's an important piece here to understand. So although we're coming up with centimeters cubed, another word for that is cubic centimeter, the box that we make in a cubic centimeter fills or has the same volume as 1 milliliter. Pretty important type of unit understanding there. Now, so we're going to measure the dimensions and then we're going to calculate based on the different formulas. Now, the second part, the second objective, is we're going to measure the mass of the four objects using a triple beam balance with our rules of measurement and significant figures. We're going to also do what? Calculate their density. Okay, so we're going to have the volume that we calculate and we're going to give birth to numbers using a ruler, and we're going to calculate those dimensions, and by calculating we're going to round according to significant figure rules, and we're going to take that dimension and then we're going to use that volume with the mass that we measure with the triple beam balance. We're going to calculate another value called density, and density is what we call an intensive physical property because it helps us identify objects, because every compound, every chemical formula, whether an element or a compound, has a unique density. Okay, and so number 3 is we're going to identify the four objects based on their density, and we're going to determine the accuracy of our results. Now, page 10 of our notes, accuracy depends on how close you are to a known value. So if you think is gold, and it's not, because if it was, it probably wouldn't be still here, but if it was gold, and I determined it to be gold because it was of the four objects the closest to the gold value that I get in my known values list, okay, how close is this to gold? So how accurate are our results? If this is 100% gold, shouldn't I get in my laboratory procedure a value that is exactly the same as the values that we report that are known for these types of elements or compounds? And the answer is yes. But with every experiment and every time you measure, you're going to have some error, right? Every measurement device, there's an error part to it, and it's associated with the guess. So we're never going to be 100% accurate, but we do want to know how accurate, and the percent error measures that, and that's what we're going to practice here. So this is a very simple lab, but one that goes over all of the important parts to the first module, the first part of the course. So we'll get into some measurement next. Now we're going to measure the dimensions of the rectangle, length, the width, and the thickness to calculate its volume. And do your best to measure each of these dimensions as I show you with the ruler, understanding that we're going to look all the way down to the edge of the ruler to get the value that we need. And it's, again, not so easy with the video, but do your best to get your best measurement, and make sure we're dealing with the appropriate units when you write them down, and of course all the numbers on the device plus that one guess. Okay, and as we look at the thickness, same idea. We're dealing with the camera's perspective issues, but all the way down to the measurement ruler. Try to find all those numbers, and make sure you give me your guess. And all your numbers here on the measurement device should have the same level of precision, same level of decimal numbers. All right, so take our first rectangular block. We have zeroed out our scale. Notice our zero line is approximately at 0. It should be perfectly there. Okay, the camera kind of gives a different interpretation sometimes. But here we go with my... And now I'm going to move the riders and get up close and personal to see what the values are. Alright, so I'm up close and personal with the first rectangular block, and now I'm going to move the riders. Okay, I can see that the weight is making this go all the way above 0, so I'm going to try to move the riders to the right to balance this off. That's why they call it a balance. Okay, so if I move this to 100, see that it only goes down, so 100's too much. So I'm going to move this over, maybe at some point. There we go. Let's try 40 grams. It's too much. This is a gram balance. 30. Okay, so 40 was too much. 30 too light. So now I'm going to go move the single one. So we got 1, 2, 3, 36, 37, 38, 39, and 39. We see here it's still not high enough. If I go to 10, it stays down. So it's 39 and something else. You can see it's not low enough. Now I got to put so I got 39, and now I'm going to move this rider, this little tiny one that moves by tenths. All right, actually a hundredths of a gram. So I'm going to move this over. See what we have. You see that coming down nicely. In fact, that's almost at 0. And it's approximately at 0. I'll move it back a little bit. And these are pretty precise pieces of instruments, because you can see that if I'm moving it by individual hundreds, my guess must be in another decimal place. So I'm still too high, so move it back. Where do I fall here? Looks like I need to go forward a little bit, and that's the game you play to balance it off. Now I'm not going to do this for the next 4 ones. I'm just going to have it balanced for you. You're going to go ahead and do that, but this is how we use a gram balance. Now, a lot of our labs will have the electronic scales to be used. I'm getting closer. Alright, and again, you see, pretty precise piece of instrument. Tiny little movements are causing this. So that's, let's say that's good enough. Let's just, I guess I can just move it just a hair. Too much. That was more than a hair. It's a thick hair there. Alright, so let's just for intensive purposes, call it there. So I would read this to be 39.1. I don't know if you can see that little arrow there is pointing in between. So it's 0.1, and then it's 0.1 what? Well, 0.1 we're certain of the 0.5, so this is 0.4 we're certain of. So where does it go in between those two lines? So my reading here is 39.14, and now my guess would be 2. Yep. So 39, right? 39.142. Notice I'm at the 3 decimal places with my guess. Okay, so for the next 3 objects, I'm just going to have the mass all set up for you. Just going to read it. Okay. So this is the second rectangular block, and we're going to measure the dimensions the same way we do number 1. Notice it has a different color and a little bit different shape, but it's still a rectangle. And again, all the reasoning for measurement is to try to come up with a volume, and then using the mass get a density to identify what this compound is. But look at the edge here. Make sure we measure right to the edge. Okay, again, we're dealing with perspective issues. And we're writing down these numbers that we get from the centimeter ruler with the appropriate level of precision, correct number of decimal places. Okay, and do your best. I know it's tough with the video, but make sure we're writing the same number of decimal places for each of these measurements, since we're using the same what? The same ruler. Okay? Again, and this, of course, the thickness, and I'm just turning it over to show you that again, it's probably very similar, but we can't assume. Okay, make sure again we write our number and the unit in the reference table, in our lab data section, that I'll show you at some point later in the video. So here I have the triple beam balance measuring out the second rectangular block. Okay, and please make that reading. I'll help you. This is on 70. Okay, and notice this rider's on a 0, and then you can make your reading from this point forward. Okay, so again, this rider would say 70. Alright, this of course is on the 0, and then I want you to make your reading. And of course, because we're using the same device, the precision should be exactly the same, meaning the number of decimal places should be the same. And of course, the unit here is grams. Alright, so that is the second rectangular block. So here we have the cylinder, and we're going to make our best guess measurement of its height, and do your best to come up with the most accurate measurement with the correct precision. Remember, those things mean they mean different things. The precision is how small and how correct your numbers you're getting from your device. Accuracy is how well the ruler is working, like if the ruler had a chip. So we should have our nice little height there. So now we're going to go after the diameter. Now you probably can see there's a problem with me going after the diameter here. And of course the problem is, where is that center? So I could probably make my best guess here and just try to go over and try to come up with a number that makes sense. I can move it back and forth. You can see where the greatest value is. Try to come up with a radius for that. Okay. Well, that's a diameter. We actually measured the radius, of course, would be half that. Alright, so now we have those dimensions which we can use to calculate our volumes using the formulas. Okay, so this is the cylinder. I have purposely moved the angle. You're going to have to assume that I have properly balanced off. Okay, this part is balanced perfectly. So how would you read this balance? Okay, and you're making your best guess. Okay, on this end here. Okay, so make your best guess there. Obviously, you always have a guess, but that is the balanced out reading from the triple beam balance of the cylinder, and come up with a mass that's appropriate for this device that's using to measure. going to measure our cube now, and we can do this a couple different ways. We definitely are not going to measure this once and say, oh, cubes have 3 equal sides. We can't assume that in lab. We have to test everything. So there is my value there. Make your best guess, and if you don't like my hand moving, certainly stop the video to come up with your best measurement. There's one side. Okay, here's another dimension. Whether you call it thickness, height, doesn't matter to me, or length. So there it is here. And then we're going to go for this dimension here. And try to make your best measurement, the most accurate measurement with the best precision possible. And the best precision, of course, depends upon my line, so you really can't. Correct precision is reporting the correct number of, that's in this case, decimal points after, or numbers after the decimal point. Okay, so now we have our measurements. Okay, we can now calculate the volume. Okay, so this is the reading scale for the cube. All right, so do your best to make your best reading. Again, using the same piece of equipment, so therefore my precision should be the same, and units are of course the same. And from these mass values, we should be able to put them into the density formula and come up with density. I would like to walk you through the calculations here. For the first rectangular block, you're going to have 3 other objects to do, so you get an idea of what's expected. And of course, this isn't so bad. This is pretty straightforward. Hopefully you're finding that. Any case, we've already measured the dimensions of this rectangular block of an unknown composition, and we have our length, width, and our thickness. And if you have numbers that are similar but different, especially our guesses, that's okay, because we're not always going to come to the exact agreement on the guess. Our numbers should be close. And remember, precision is a bunch of people measuring the same object, okay, and getting similar results. The result that will be different will probably be just the guess only. So we should be pretty similar here. And again, if you're a little bit off, that's okay. Measuring from the video is not the easiest thing and not the most accurate way. Remember, accuracy is the known, and precision, okay, speaks to how well a group of numbers are going to be similar based upon using the measurement device correctly. So in any case, we have the same measurement device, therefore we get the same level of precision decimal places. Notice I have a unit with every number written. That's something new this year, and you must always have a unit. Number without a unit is wrong. And then of course I have the mass out using a different measurement device. Gives me a different level of precision. Our triple beam balance are very precise instruments. Okay, so now that we have our dimensions and we have our how can I say, mass, we're going to come up with density. Now we know that density, okay, is equal to mass over volume. So we already have our mass, but we don't have our volume. So the volume of a rectangle, okay, volume is equal to length times width times height. So we're going to essentially put our values in for that formula. For the other objects that we're going to do, the 3 others, you have the formula on the first page. So I have calculated the density using my dimensions, length times width times height, and I came up with 15.478876 centimeters cubed. Notice centimeters times centimeters times centimeters is centimeter cubed, in which you're going to get a cube. You're basically going to get a volume, which is the space something takes up. That's what volume is. And a centimeter cubed is a volume unit. And it's equal to a milliliter that we're going to use in the next lab. Any case, so 15.478876 has way too many numbers. Remember, we have to be able to round this number to the correct number of sig figs because it's the accuracy rule here. Multiplying numbers, we have to get rid of the weakest link. And the weakest link is, well, we have numbers with 2 significant numbers. That's the weakest link. and this number has 3 and 3. So our number that we're going to report in our lab manual cannot be more significant than our weakest link, which is the number with 2 sig figs. Remember, leading zeros don't count, so non-zero numbers, this has 2 sig figs, right? This has 3 sig figs, and this has 3, so it makes sense that our answer cannot be reported with this much precision. If we write this number into this space right here, we're saying that we're sure of all of these numbers, and this would be my guess. We can't do that. We are not sure of all these numbers. We're only sure of 2 of them. That's right. We're only sure of 2 of all these numbers. Only 2 of these are significant. Remember, the numbers report in a lab manual reflect the types of instruments that were used to gather that data. So because we used an instrument that only had 2 sig figs and one of the 3 that we calculated with, then therefore we should only come up with 2 numbers that we can speak to in terms of significance. So we round to 2 significant numbers, our weakest link. We look at this 4. It's less than 5, so this becomes 15 centimeters cubed. Notice the unit's different, okay? And I have a unit. All right, and that's what we do here. Now, density is mass over volume, and as we continue to do this very simply, I'm going to put the mass that I got from the measurement device. We gave birth to a number by measuring that mass, and we're going to divide by the volume, which is 15 centimeters cubed. Really, really important to use our units here to see what we're going to get here. I'm going to get a number that's equal to grams over centimeters cubed, just like over here. It's grams. Now, grams over means grams per. Of course, it's a mass per volume. So I'm going to put this into my handy-dandy calculator, and I will get myself a value for density. And when I do so, I get 2.609466667 grams per centimeter cubed. I do not write all of these numbers because all of these numbers are not significant. Where is my weakest link? My weakest link is 2 sig figs. That comes from where? This measurement here. It always trails back to the measurements, right? If we're calculating something in lab, the numbers were given born by the measurement devices, and the measurement devices tie us to our final result. If my least significant device is here, then my answer is going to be as significant as its weakest link. This only gave me 2 numbers from the measurement device, so I can only be sure of 2 numbers. And that's why the total result should be rounded to 2 numbers. Notice the 0 is the next number. It's less than 5, so I round this to 2.6. Now, what I will say as we go on, and I want you to do the lab this way, as we get to more complex mathematical problems, and we will eventually, especially in AP Chem, we're going to probably round just once at the end. Every time we round and multiple times, we kind of get rid of maybe important numbers. So what we would do in a real AP problem is we'd probably carry this raw number into the bottom and then round to 2 sig figs at the end. But in terms of this exercise, this lab, you can round twice. Now, once I have my 2.6, what we're going to do in this lab is we're going to figure out what this object was. What's the composition? I've got a density. Now, density is a physical intensive property. We can actually identify compounds and elements based on their unique density. So when we go to a table like this one that shows me the known values in this lab, I came up with 2.6 grams per centimeter. If you look carefully on this graph, you'll see that the one that's closest is the aluminum, 2.70. And look at the units, grams per centimeters cubed. So the only one that's closest is aluminum. So we've just identified the first rectangular block to be aluminum based on calculating density. And at some point in the lab, I'm going to ask you to do a % error using this known value and this experimental value and see how close we were to the known value. It's a measure of accuracy.